Hey everybody, this is Kirby White here to do a quick overview and example for using the Mahalanobis Distance. I'll talk about what it is conceptually and then we'll do a quick example in R. And before I begin, it's probably important for me to say that what I'm going to describe is conceptually accurate and helpful, but it's actually technically inaccurate. And the reason that I'm doing that is because it fundamentally is requiring an understanding of things that we haven't covered yet, like eigenvalues and eigenvectors and matrix algebra and covariance matrices and inverting and decorrelating variables. And that's some stuff that we're going to get to a little bit in psychometrics. So just put a pin in that for the future if you want to come back to this topic and really understand mathematically what's going on. But for right now, it's really unnecessary for our ability to use it well. So let's go ahead and jump in. First, let's describe what outliers are real quick and just why they're important to identify and deal with. They're extreme data points, and so here you can see a distribution of data, and then there's one value that's hanging out here way far away from everything else. And what that does is it kind of shifts the distribution out of normality, but probably more damaging for our analyses is that it skews the mean and the median away from each other. And so it brings the mean towards the outlier while mostly leaving the median in place. So here you can see that the median is still at the center of the majority of the data set, but the mean got pulled way out here. And so if you were just to look at the average value of something, of this data that's represented here, it might be artificially high, and you may not recognize that if you're not looking for outliers. You'll just take the mean and move on. But anyway, this is a review, so let's talk about what we would do or how we would identify or define an outlier. There's multiple ways of doing it, but for our purposes, I think we've pretty much stuck with creating a threshold of values that are plus or minus 3 standard deviations from the median. So in a nice perfect world, when we've got this distribution of our data, we can set a threshold at 1, 2, 3 standard deviations above the mean and 1, 2, 3 standard deviations below the mean. And any values that are larger or greater than those thresholds, we would need to deal with somehow. We could either delete it just entirely, we could truncate it to still a large but not as large value. We might just include it in our data set with a caveat that we know it may affect our analyses. It really depends on what you're doing. So that's a common threshold for identifying what an outlier is. Now let's talk about some issues and limitations with the univariate analysis for outliers. So imagine that we have this data set. It's just a scatter plot of 2 predictors. So we've got x1 and x2, and I'm specifically not calling it x and y, even though I may make that mistake in this video. But I'm calling it x1 and x2 because these are both predictors. Y, for our purposes, is usually reserved for outcome or dependent variables. Now let's imagine that we've got these 2 data points in here, these orange ones. Now, using your univariate analysis for outliers, you're not going to be able to detect either of these points, these orange points, as problematic, because if you're only looking at one variable at a time, for instance, this point's x1 data set is, 7 or 8, and that's perfectly in range. It's not even the largest value of x1 of data for x1 in this data set. Same with x2, its x2 values maybe 2 or 2.5, and that's not extreme at all. And same goes for this one. So really, if you're only looking at one variable at a time, these data points aren't going to stand out at all. There's nothing special about them. It's only in combination with each other that they become unique and problematic. It's that we've never seen in this data set. This is the only point where its x1 value is 8 and its x2 is 2. That's just not common. Normally we see them, closer together. And so if you plotted these on each variable on a density curve, like you can see over here, nothing's going to stand out to you. So this is really a limitation of the univariate analyses, is that it completely overlooks the combination of variables. And in this example, I'm only using 2 variables, but that's just because we can graphically represent it pretty easily. But the Mahalanobis distance, which we're going to get to in a second, the solutions for this are really, you can use any number of variables. And so this example we're using 2, but you could easily use these same solutions with a data set that has 5 or 8 or 10 or 15 or any number of variables in it. So let's talk about the Mahalanobis distance now. This is the solution to that univariate problem, and it requires 3 components to calculate. The data set, and so for this example we'll just use the one that we've already talked about and that is shown here. It also needs the mean scores for each variable, and so that's the dashed lines here. You can see it, this is kind of roughly the mean score for x1 and the mean score for x2. And if we stopped here, well, never mind, let's talk about the third point. It also requires the variable covariance, and that is kind of like a correlation, but it's in raw units. And the covariance is what tells the algorithm how we expect the 2 variables to relate to each other. So let's take this point in the top right for a second and talk about it. It's pretty far from both means. It's pretty far off the x2 mean. It's much larger than it. And it's pretty far away from the x1 mean. So if we calculated its distance from the mean, this point is looking kind of like an outlier. It's pretty far from the mean. But when we take that covariance into account, it's basically right on that line. And so that's how the algorithm kind of knows that this point is not going to be problematic. Yeah, it's far away from the means, so it should have a higher score than, say, this one, which is really close to all 3 of these lines. But now it's really obvious why these orange ones should stand out as outliers. It's far less than the x1 mean. It's far greater than the x2 mean, and it's nowhere near the expected value given the covariances for x1 and x2. So this is kind of a visual way of representing what the Mahalanobis distance is looking at. And what would happen when we calculate it is it's going to load up the data set, and it's going to create a score for each data point, each row or record that's in your data set. And so here, this top right one, maybe it has a score of 5, and these are completely made up numbers. But maybe it's got a score of 5, which is okay, and the points that are close to the center may be, really close to 0, less than 1. And this one down here is 5, but now these points out here are far greater. They're sort of punished for being far away on all 3 axes. And so that's why their scores are 15. And what we could do is use the Mahalanobis function to calculate these points, and then we can sort of stack rank them, and it becomes super obvious that we've got 2 data points, 2 combinations of scores that are pretty drastically different than all the other combinations of scores in the data set. And now we could go back to our original metric for identifying outliers and calculate the median and the standard deviation for the Mahalanobis distance, and find scores that are greater or less than 3 standard deviations away from the median. And so once we calculate the Mahalanobis distance, we can then kind of use it as its own variable on its own. So let's go ahead and jump over to R, and I'll show you how to calculate it over here. You'll be able to download this file, but it requires 2 packages, tidyverse and pastx. Tidyverse is just a cleaner way of writing our syntax, and pastx gives us our descriptive statistics. I've gone ahead and created this data set, which will just serve as our example. And so when you run that, it creates the object up here, df, short for data frame. And let's do those univariate analyses we talked about. We'll look at the descriptive statistics for x1 and x2. And you can see that their median are pretty much the same, maybe 4.9. And if we look at the standard deviation, we'll just talk about x1, 1.4. I'll just round it to that, 1.4. And so that times 3 would be 4.2. And so normally what we'll do is look at the median, 4.8, or 4.9, and we'll add 4.2 to that. So what is that, 9.1, I suppose. And and we'll look for any values that are greater than 9.1. And there aren't any. The max value here is 7.2. Likewise, we could subtract 4.2 and get, what is that, 0.6. And we can see from our minimum value that there aren't any data points that exceed that. So this is just pointing out that according to the univariate analysis for the standard deviation threshold, we don't have any problems in x1 or in x2. Normality is not required for this, but we can go ahead and check. And so x1 and x2 both have acceptable p-values. Maybe they're a little bit smaller than we'd like, but they're greater than 0.05, and so we're going to go ahead and just assume that these in fact are normally distributed. And let's create the histogram or the density curve for those, just to go ahead and look at it and see if there's anything else that's unusual about this. And nope, x1 and x2 are both looking pretty good, normal enough for us. So our conclusion so far is that both variables are great for statistical analysis. There's no outliers if this is where we were going to stop. So now let's do the Mahalanobis distance and calculate that. So what this is going to do is create a new column in DF called MD, just short for Mahalanobis distance. And here's the function. It's just called Mahalanobis, and you give it the data points, the column means, and the covariance matrix for the variables. And just for ease of reading, we'll round it to 2 decimal places. So that has created it, and now let's just take a look at the top few rows. We can see our x1 and x2 values and the Mahalanobis distance scores that have been calculated for these. These seem pretty reasonable. 3.04 might be a little high, maybe, but we'll be able to check that and look at the descriptive statistics for that new variable, Mahalanobis distance, and we can see that the median is 1.64. Our standard deviation is 1.68. Maybe we'll round that to 1.7. And that times 3 would be 5.1. And so if we take 1.64 and add 5.1, we get 6.74. And if we look at the max values, 9.4, we can see that there's at least one Mahalanobis distance that exceeds that threshold that we just came up with. It doesn't look like we'll have any problem with our minimum values, but this is kind of the first indication that there's something going on here. So let's move on to the density curve and see if we can plot this and see a little bit more about what's going on. This is the distribution of the Mahalanobis distance scores for the entire data set. You'll see that the bulk of them are kind of below this 6.0 or 6.25 layer. That's the majority of them. But there's this tail out here. There's a few that look very high compared to the rest. And so now we can see there's definitely something going on out here. And so let's go back to take a look at this. That means that in this column there's a few scores that are pretty high. And this line of code I'll just talk through real quick. What it's doing is creating a new variable in the data set called MD outlier. And what we're going to do is use an if-else command to set it to either true or false depending on the score. And what it's doing is saying if the Mahalanobis distance is greater than the median plus 3 times the standard deviation, if that is the case, give it the value of true. If it's not, give it the value of false. And so I'll run that real quick, and then let's take another look at the top few rows. So this is showing us this new column here, which is just identifying for us really easily whether or not we think that this Mahalanobis distance score is an outlier. And let's take a look at just the outliers, and we can do that by saying print df, but only where MD outlier equals true. And sorry, I got to throw a comma in there. And so when we do that, this is now showing us the 2 rows that appear to be problematic with the outliers. So here's the x1 and the x2 scores and their Mahalanobis distance, and the indication that we calculated that this is in fact an outlier. And so now we could move ahead with our research and decide, what do we want to do with these points? Do we want to change the data that's in here, drop these entirely? Totally up to you and whatever is required for you to have the best research possible. But now the conclusion based on this Mahalanobis is that we've got two participants or 2 records in our data set that are outliers. Not univariate outliers, but multivariate outliers. So it's the combination of their scores that's problematic in conjunction with the other scores that are going on. Now, like I said earlier, we could put this on a scatter plot, and because we're only looking at two variables, it's really easy for us to put this up and just intuitively know, hey, we've got two problematic data points in here, but we could not visualize it this way if we had 5 variables that we needed to calculate the Mahalanobis distance for. And so that's why it's important to go through those more quantitative steps instead of just looking at it visually, because in any combination of those 5 variables, everything may look normal, but you're just not able to see those data points as outliers. So anyway, I hope this was helpful, and I will see you next time.